In the last week, we have talked about the pod kinematics using the POE. At that time, we have derived this kind of a pod kinematification as a product of a matrix exponential. Okay, now we will talk about the velocity kinematics and the statics. So the velocity kinematics will deal with the problem of calculating the twist of the end effector from a given set of joint position and the velocity. Okay, let's consider for the kinematics here. Okay, let's take the time derivative of both sides. Okay, x dot. Because the for the kinematics is a function of the joint position, so it should be applied. The chain rule should be applied both sides. Okay. In here, round if f is a column vector. Okay, Fm. The round zeta transpose implies the derivative with respect to zeta in the low direction. Okay, because it implies the low vector. So the first element will be the round f1, round zeta 2, blah blah, and then we will arrive at the round f1, round zeta n, like this. The final element will be the round fm, round zeta 1, and the round fm, round zeta n. So we can get the n by n matrix. This kind of matrix is denoted by the J here. Okay, it is called as Jacobian. Okay, the Jacobian matrix represents the linear sensitivity of end effector velocity x dot to the joint velocity zeta dot. So this mapping, the Jacobian mapping, shows the relationship between the two different space x dot and zeta dot. Okay, but we should notice that the J is a function of a joint variable, not a joint velocity. Okay, let's take a concrete or detailed example. In here, the endpoint of the dual robot system is obtained. To obtain the pod kinematics, let's apply the sine and cosine. Okay, this is the Aaron cosine zeta 1. This part is the Aaron L2 cosine zeta 1 plus zeta 2 because this is the zeta 1. So we have this equation. As a similar way, we can get x2. Okay, let's take the time derivative both sides, x1 dot, and then we arrive at this equation using the chain rule. This is also we can get it. Okay, in these two equations, we can collect all the components according to the zeta 1 dot and the zeta 2 dot. So in here, this term and this term appears proportional to the zeta 1 dot. So we have the first element. How about the zeta 2, the 1 by 2 element? It depends on these terms. Okay, so like this, we can construct the matrix. Okay, this is Jacobian. Okay. Okay, let's assume that each column vector as a J1 and J2. Okay, this column vector is denoted by the J1 and the J2. Okay. In the geometric viewpoint, J1 implies actually the zeta 1 dot is obtained like this. Here, let's draw the perpendicular, let's draw the straight line to the end effector, and the orthogonal direction will be the J1. Okay, how about the J2? J2 will, it depends on the zeta 2 dot. Okay, theta 2 is like achieved like this. From this this direction, we can make the orthogonal part, okay, like this. J2 will be achieved in this orthogonal direction. Okay. From this geometric interpretation, we can get some insight. Okay, this is the base, first joint, and then the effector. Okay, here theta 1 is 0, theta 2 is 0. At that time, the J1 will be denoted by this perpendicular direction. How about the theta 2, or the J2? J2 along with the same line. At that time, we cannot move the end effector in this direction, is right? So this kind of computation is called as singularity. Okay, in here, as long as the J1 and the J2 are not collinear, both are not aligned each other, it is possible to generate a tip velocity v tip in any arbitrary direction in the x1 and x2 plane by choosing appropriate joint velocity theta 1 dot and theta 2 dot. As mentioned before, theta 2 is 0. At that time, J1 and J2 will be collinear, will be aligned each other. It is not dependent on the angle of theta 1, because if you change the theta 1 like this, keeping the theta 2 as a 0, at that time it's singular, because J1 and J2, I'm not sure the direction of, but both will be aligned each other. Okay, okay, let's calculate. If the theta 2 set to be 0, here, this is 0, this is 0, this is 0, and 0. At that time, J1 will be this one. J2, this one. From J1 and J2, we can know that there is some proportional relationship with the proportional constant. So J2 can be expressed using the J1 with the scalar multiplication. So it means both are indicate the same direction. Okay, as a numerical data, let's apply the LRL2 and the theta 1 and the theta 2. At that time, we can get the numerical Jacobian matrix. Okay, so let's assume that the both motor, the maximal speed of electric motor attached to the theta 1 and the theta 2 are bounded as 10 radian per sec. Okay, that is the assumption, but it's very reasonable because the every motor system makes use of the harmonic gear to reduce the speed. So 10 radian per sec, it's a good number. It's a very practical number for actual electric motor system. Okay, the maximum speed is bounded. Theta 1 max as 10, theta 2 max as 10. Okay, this data, this limitation of the electric motor located here, okay, in the space of the theta 1 and the theta 2. Okay, using the Jacobian, this 10 and the 10 point will be mapped to the minus 1402, 2402 here in the x1 and the x2 plane. Okay, using the Jacobian, this data will be mapped here. On the other hand, minus 10 and the 10. Okay, minus 10 radian per sec plus 10 radian per sec here. Both data are applied to the electric motor. Maybe this point is will result in the 0 and the minus 10. So this point we will map here. Like this, we can write down some polygon like this in the x1 and the x2 space, and the vector plane, and the vector velocity should confined or limited in this plane, in this scale, in this polygon. Okay, if you assign some point outside this polygon, we cannot achieve using this kind of motor. So it shows the performance limitation in viewpoint of the velocity. Okay, this kind of polygon is not a general concept, so we will introduce some unit circle to indicate unidirectional, omnidirectional characteristics. It means the every okay, this point is the 1 radian per sec in viewpoint of the theta on top. Okay, according to the angle variable, we can write down the unit circle equation. Okay, it is not performance limitation in viewpoint of velocity, but if you multiply the some proportional constant to indicate the maximum speed, at the time we can get some insight in the performance limitation of an n-vector plane. Okay, so this kind of unit circle will be applied to the Jacobian to obtain the limitation, the shape change, in order to obtain the concept of a shape change of a circle. Okay, unit circle will be the x1 dot square plus x2 dot square will be 1. In this case, we can replace as a cosine alpha and the sine alpha. Okay, the cosine alpha and sine alpha will be applied to the Jacobian. At that time, x1 dot and x2 dot is obtained. To get some insight from this equation, we will apply the numerical data. Okay, as a 0 alpha, this point will be applied to maybe this point. I'm not sure. Anyway, we can get when the alpha is set as a 45 degree. Okay, maybe the -1 same point. So maybe this point 45. This point. Like this, we can indicate every point according to the variation of the unit circle. Maybe this shape will follow the ellipsoid. Okay, so this circle maps through the Jacobian to the ellipsoid. In the space of the tip velocity, it is called as manipulability ellipsoid. Okay, manipulability ellipsoid is defined by the Juneo Yoshikawa in Japan. Okay, actually, he developed this kind of concept to denote how far its posture from the singularity. Okay, as the manipulability configuration approaches the singularity, ellipsoid approaches to the line segment. Ellipsoid is collapsed, and then ellipsoid will be the line segment. Okay, if you this configuration is changed to the straight line, at that time the Jacobian will be this line. It means we can move this direction, but we cannot move this one. Okay, so this ellipsoid will be changed into the line segment. Okay. Okay, Jacobian has another role in the static analysis, not velocity analysis. Okay, suppose that an external pulse is applied to the robot tip. Okay, this is the base. Robot is like this. Some pulse is applied. It is called as F tip. Okay, this is the tau 1 and the tau 2 here. Okay, here, this point the velocity is the Vt, and it's theta 1 dot and theta 2 dot here. Okay, here the conservation of power. Before that, we should assume that this posture is a static. This is not moving, so static in equilibrium. This kind of assumption is required because if this robot moves, inertial force will appear. Okay, the inertial force is related to dynamics, so we will the problem to be very limited situation. So we will assume that the robot is static. Robot is not moving. Okay, but the robot has the external force and T velocity. Okay. Okay, the conservation of power. Okay, the FV will make some power as a unit of the Newton meter per sec. Okay. On the other hand, in the rotational space, we can get some another power that will be tau transpose theta dot. Okay, should be equal to F transpose V in the T part. Okay, it is called as conservation of the power. Okay, here, as you know, the end effector velocity will be replaced with the Jacobian, Jacobian and the theta dot. And by comparing both sides, we can know that the tau should be equal to J transpose F T poles. Okay, some robot as the external pulse Ft, at that time the tau 1 and the tau 2 is required to maintain the static posture. On the other hand, let's assume that the gravity is applied. Okay, in order to maintain the posture of the robot system, the gravitational torque should be applied to the robot, to the electric motor. That can be calculated using this kind of concept. Maybe it will be very useful. Okay, in here's Jacobian transpose, the inverse of the Jacobian transpose exists. At that time, the inverse relationship is obtained. Okay, let's consider again the numerical data. This is Jacobian. Okay, Jacobian transpose can be used to obtain the static torque, static joint torque to maintain this kind of end effector poles. Okay, the inverse of the Jacobian transpose exists. At that time, we have this relationship, inverse relationship here. Okay, here we know the electric motor has some torque limit. Okay, if the maximal torque of the motor bounded as 10 Newton meter. Okay, it's not reasonable because the many electric motor equipped installed in the manipulator has the 100 Newton meter. That's normal. Yeah, this is very small. Anyway, the 10 Newton meter and the 10 Newton meter is applied to here. And then Jacobian inverse transpose mapping will have minus 14.1 and 0. So we have this point. B point, minus 10 and 10 will have this point. Like this, we have some polygon. This polygon is related to the end effector T-poles region. If you assign this kind of T-poles, we cannot achieve using this motor. Is it right? Because the region of this is the performance limitation. Okay, so if you have the robot, if you know the electric motor capacity, such as the velocity, maximal torque. At that time, we can get some polygon to achieve the end effector velocity and effector pulse. Okay, this kind of Jacobian inverse transpose can make another concept. In here is pulse ellipsoid. In order to define the pulse ellipsoid, we will use the unicircle torque. Okay, the torque is located on the boundary of unicircle, tau 1 and tau 2, and then we will apply this point to obtain the pulse ellipsoid using the Jacobian inverse transpose mapping. Okay, as mentioned before, tau 1 will be replaced as a cosine pi and sine pi. Okay, as you know, this is post Jacobian inverse transpose. Okay, by applying the unicircle boundary of the torque plane. Okay, 0 alpha at the time we have 1 1. Maybe the 1 1. This point will be this point will map to here. Okay, minus 1 0, minus 1 0. Maybe this point. So like this, we have some ellipsoid. Okay. Okay, this pulse ellipsoid illustrates how easily the robot can generate pulse in different direction. Okay, in order to obtain the manipulability ellipsoid, Jacobian is used. On the other hand, to obtain the pulse ellipsoid, Jacobian inverse transpose is used. Okay, maybe you can assume, you can know that the relationship between both the Jacobian inverse and the transpose is used. It means both ellipsoids are orthogonal each other. Okay. So let's summarize the pulse ellipsoid and the manipulability ellipsoid. At this posture, okay, 0 and 45, 0 and 45, the Jacobian and the Jacobian inverse transpose will show this manipulability ellipsoid. Okay. In here, this direction is the major axis. This is the minor axis. Okay. Okay. These two axes are maintained in the pulse space, but the length, the major axis length and the minor axis length, should be defined using the reciprocal property. So this is the very long. At that time, the small one will be achieved. This is very small, very long direction, very long component will be achieved because both are orthogonal each other. Okay. Okay, let's read this full concept or the summary. As is evident from the manipulability ellipsoid and the pulse ellipsoid, if it is easy to generate a tip velocity in a given direction, okay, it's very easy in this direction. At the time, it's difficult to generate in the same direction because the pulse ellipsoid is orthogonal to the manipulability ellipsoid. Okay, the same direction. On the other hand, it's very difficult to move in this direction. At that time, the pulse can be generated using this posture easily. So it's hard. It's easy. Like this, both relationships are has the reciprocal property. Okay, for given robot configuration, the principal axis of manipulability ellipsoid, this one, and the pulse ellipsoid are aligned each other. This is major, this is minor, and length of the principal axis of the pulse ellipsoid are reciprocal of length, the inverse length. of the principal axis of the manipulable ellipsoid. Okay, the inverse relationship is used. Okay, at a singularity. Okay, singularity. This ellipsoid will be the line. Is it right? That means the anti-vector will move this direction, but it cannot move the orthogonal of line segment. Okay, this line, in the case of the pulse ellipsoid, we have this line. Is it right? So, manipulative ellipsoid collapses to the line. The pulse ellipsoid becomes infinitely long. Okay, in the direction of the orthogonal to the manipulative ellipsoid. Okay, so both in the case of the singularity, the manipulability and the pulse ellipsoid are orthogonal each other. Okay. Okay. In the in the practical applications, if we want to carry the heavy suitcase using your arm, at that time we are stretched down. Our arms are stretched down to the gravity. At that time, the elbow is extended to the 180 or 0 degree. It means singularity. Singularity implies this arm cannot move in the gravitational direction, but the pulse can be sustained in the same direction because the pulse and the manipulative ellipsoids are the reciprocal or orthogonal each other. Okay, consider carrying a heavy suitcase with your arm. It is much easier if your arm hangs straight down under gravity with your elbow fully straighted at a singularity. Okay, because the pulse you must support pass directly through your joint. Therefore, there is no requirement on the talk about the joint. Actually, we are using the singularity in carrying the very heavy suitcase. Okay,